Hi, and welcome back to another LeetCode problem. We're going through the graph problems here on LeetCode.io, and I want to tackle another problem. I want to look at the rotting oranges one. So let's see what it's about. I have tried it, 3 years ago. So yeah, let's have a quick look at what this is. I really like these kind of graph problems. They're actually quite easy to solve. So maybe we can one-shot this one. Right, so we're giving a m by n grid where each cell can have one of three values, 0 representing an empty cell, 1 representing a fresh orange, and 2 representing a rotten orange. Every minute, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. Return the minimum number of minutes that must elapse until no cell has a fresh orange. If this is impossible, return -1. No cell or no empty cell? So, okay, so here we start where we have the grid. We start with minute 0 with 1 rotten orange. So that's the 1 in the grid, I guess. And yeah, at every step, let me just copy this so I can draw on it. So we start here. We start here. After minute 1, we can mark these neighbors as rotten. Then in minute 2, we would mark these neighbors as rotten. Minute 3, that neighbor gets added, and minute 4, that one. Okay, so 4 minutes. So this looks like a classic BFS approach, where you just keep track of all the oranges that were rotten in the last step. But at the same time, you have to start with all of the oranges that are rotten according to your grid. So I think that's going to be super easy. So we have to have one pass above across all rows, all columns and all rows in our grid to collect all of the rotten oranges, and we put them into a queue, all of their positions, and then we just iterate with the BFS over that queue until, so breadth first search, right? Until the queue has no more elements. And the number of iterations that we had to take over the queue is then our result. That's pretty much it. So yeah, let's dive right into it. So we will have, well, I should say what the runtime complexity is. So in the worst case, all oranges are rotten. Well, all cells have an orange, and one orange in the corner is rotten, so that we have to actually visit all cells, and all of them get rotten. Now the worst, well, how many cells can you have at most in your queue, right? Because we're going to reuse the grid. Can we reuse the grid? I think we can. We can just update the grid with the state of the orange, right? So we don't need extra space to store the state of rotten versus non-rotten. So that's nice. But we have to store the elements in this queue. And what's the maximum amount of elements we can have in a queue? Well, if we have a rectangular grid, width and height, right? And we start at the corner, and then we basically, our breadth first search queue contains the elements that are on the frontier of the exploration as we explore through this area, as we did here, right? There we are. Let me say, so first we just had 1 in it, then we had these 2 in it, then we had these 2 on this, and then we had this one, etc. So you can see that depends on how many cells you have on the diagonal. And if it was a square matrix or square grid, we would have a square root of n elements at most in terms of the space complexity. Otherwise, the maximum number of elements would be I guess it's the minimum of the width and height, but the square root of that. Isn't that correct? If we had, let me just check. Let's pretend that these are connected, right? So we have 1, 2, 3, but we'll never have more than 3 cells if we do this. So actually, yeah, it's the minimum of width and height, and then taking the square root. That's going to be our space complexity. And time complexity is going to be, well, width times height. So yeah, so let's write that down. Time and O of square root minimum. Oh, I mean, minimum or maximum doesn't really matter because n plus m is the same. It's linear. Well, I mean, n plus m is the same as just the minimum of n plus m. It changes the number by constant factor. So for the O notation or for the asymptotic analysis, it doesn't make any difference whether I put min of n plus m or just n on m. So anyways, yeah, let's keep it this way. So, right, so we need our little loops, but before that we need to know what the width and the height are. So the width is the length of the first row. The height is the number of rows in the grid. Now we have our little for loop for x in range width, for y in range height. And if grid at position y, x, remember first select the row, then select the column. If that is equal to the value, what is the value for rotten orange? 2, right? 2. So earlier I pointed at this 1, which was incorrect. So 2, that's the value of the rotten orange. That value is 2. We're going to add this to our little queue. And, well, we're going to use a FIFO, and in Python that's a deck. And from collection, import deck. And we're going to add this to our little FIFO. And we're going to add, what are we exactly going to add? Well, we're going to add a tuple of x and y. We also need to keep, well, we'll do that in a moment. But so now we're collecting all of the oranges that are rotting. Now the next step is, so this is a queue initialization phase. So the next thing is we need to remember which cells we have already visited so that we don't try to rot oranges again. Let me think if that's correct. Actually, in this case, we don't. We don't have to keep track of visited because we can use the grid to determine if an orange is rotten or not. And if it's rotten or empty, if the cell is rotten or empty, then we're just not going to go there. Otherwise, we're going to pick, well, the next neighbor that is not rotten from a rotten thing. So we'll have a little queue for a little loop of our queue. So while we still have elements in our queue, we need to, the rotting continues, right? So, and we need to have a result variable that counts the number of iterations. And in the end, we're going to return that. Right, so now what we will do, we will iterate over all of the positions that are currently in the queue. This is a nice trick because the length of the queue is evaluated only once. So if we now pop elements out of it, with pop left, it doesn't change or alter our loop in any way. Cool. So, well, now we need to check whether this position, well, yeah, we need to check whether that position, whether that position is actually a valid position. We only want to go there if it's not already rotten and if it's not an empty cell. So so we're going to get our x and y back from our tuple. Actually, since we're not storing our visited nodes, we don't really have to work with tuples. In the last two examples, I worked with tuples because I had to add them to a visited node. And we don't really have to do this here anymore. So we can just really put the XY coordinates as a list in there and then just pull it out like that. I mean, that would also work when this was a tuple, but I just want to make the point we don't need a tuple anymore. So we get the position, and now what we do is if grid at that position is not a fresh orange, we're not interested. Right? Now, you should see that there could be an edge case where we pop out lots of irrelevant positions and then results is actually wrongly increased. So we need a flag, right? And we'll set that to false. And only if changes is set to true, meaning there was one more orange to rot, we will set changes to true. And only if changes, then we're going to increase our result. Yeah, so that's another little pattern that you might find useful, because it all depends on what you put into your queue. You know, if you put elements in your queue that you don't really need to visit, you need to be careful when you count the number of iterations over your queue. Doing breadth first search. All right, so if that is true, well, we're going to mark this orange as rotten. So grid as y, x, we're going to set it to a rotten orange. So that's going to be 2. And we're also going to add all of the neighbors of that orange to the grid, so to the queue. So for get neighbors, and we're going to implement that in a second, neighbors of our x and y position for next x, next y in get neighbors. We're going to queue append next position. And we don't actually have to explicitly name them here. We just do like this. And next position will be an area of x and y, just like we had it in the very beginning. So yes. Now that is the queue initialization and the breadth first search. And now we need to implement the get neighbors method, a little helper method. We will put that up here. And we will have an x and y coordinate from where to start. And now in the previous videos, you've probably seen how I use zip to iterate over the x and y coordinates. Now you can also do it just with, let's say, a delta x in -1, 0, +1. And we iterate with a delta y. I also put the y in the outer loop for dy in -1, 0, and +1. Now, if we combine these deltas, right, we iterate. If this is our cell, you know, x will go from -1 to +1, and y will go from -0 to -1 to +1. So we'll actually also explore this cell, that cell, this cell, and this cell. So we're exploring all 9 cells with this approach, which is why I like the one with a single loop a little more. But I just want to show you, you know, just a different approach. You're going to need a neighbors array to which we will append all the neighbors that we shall compute. And well, we're going to append the neighbor after meeting some condition, right? So what we could say now, well, we know that the nx position and the ny position would basically be our x plus delta x and our y plus delta y. What we need to do is, well, we need to check of whether we are still in bounds. That's one check we have to do. So if nx smaller than 0 or nx is larger or equal to the width of the grid, we're going to ignore this candidate. Same for the y position, except that we have to come to check whether it's larger or equal than the height. And we also have to check, well, we don't have to perform any filtering of whether that's a valid neighbor, because we have the check here as well. We could add another check here, but it's really redundant. We don't need it. However, what we do need is we need to make sure that we only consider the neighbors. Well, we only want to consider this neighbor, this one, and that one. And we want to ignore these candidates when we have this with the 2 for loops, where our dx goes this way and our dy goes that way. So, well, how do we do that? Well, let's look very critically at this. And, well, how could we do that? Well, we don't want them to be both 0. That's one thing, right? So both being 0, dx and dy, that is not going to be nice. That will be the center position. And we also don't want both of them to be a value that is not 0 at the same time. So we want basically an XOR. We want either the x is some value that is not 0 and y is 0, or x is 0 and y has a value that is non-zero. Right? So we're going to do a little comparison. Check if the absolute value of x is unequal to the absolute value of y. That is the correct case. In all other cases where they are equal, that will fail. Let me think about this critically. So here we have x minus 1, y minus 1. So this one will be filtered out. You have x minus 1 and, here x is 0 and y is minus 1. So that'll work. Here again, we have both unequal to 0 when we take the absolute value. And same for this corner case. Yeah, I think that should work. So let's implement that logic. So if absolute value of dx is equal to the absolute value of dy, well, we're going to ignore it. Oops. Continue. That's pretty much it. So when they're both 1, both 0, we will not consider this as a valid delta to our position. Cool. So that should be everything. That should be everything. And well, I'm brave enough to run this code now. To see if it works, I have no idea. So let's try it. So we're getting the wrong answers. The output is 0 because y. If changes, return y. Okay, so now we're going into the debugging. And for the debugging, I'm going to add a little helper method. Def show grid. And that one will just simply print, well, the grid, right? So for row in grid, print row. And then we add maybe a little line break, like an empty line at the end. And we should show the entire grid. Well, and we also want to see what is in our queue. Print. That's going to be our queue. And then we're going to show our little grid. Show grid. So, right, let's run the test. Indentation error. Okay, so in our queue, we have the cell 0, 0, right? This is correct. And this is how the grid looks like. Nice. And then we terminate right away. So there's nothing else to do. Well, that is weird, isn't it? Are we not returning the neighbors maybe? Neighbors at pen. So we are returning that. -1, 0, +1. dy dx. That is all correct. What is happening here? So we're checking if the neighbor is not 1. And in that case, we continue. Okay, otherwise we're going to mark the current cell as rotten. So maybe let's print the grid after the queue. And if we don't see any updates, that means we stopped here somewhere. Right, and we see no updates. So we didn't find any oranges that we could rot, right? When we pop this cell out, let's see. If we pop this cell out, its value should be, oh, I see what the error is. So when we pop out the first cell, we know that it is rotten. That's right. And because it's rotten, we're going to ignore it. So what we should do instead is, well, if it's an empty cell, then we're going to ignore it. Otherwise, if it's rotten, it's fine. Isn't it? No, it's not. It's not fine. We need to mark this Yeah, how do we do this, right? We have our cell of all the rotten ones. Oh yeah, well, we can change our logic slightly. So what we could say, if this cell is, well, if this cell is empty, we're going to ignore it, right? Otherwise, we're going to mark it as rotten. Now, when we append the neighbors, we can, to prevent an infinite loop, we will check whether it's rotten or not. So if, and yeah, maybe we should do it right away in here. So if the cell is rotten, if grid at ny, nx is already, or is not an unrotten tomato, we're going to continue. So we're only going to explore tomatoes that have not been rotting yet. So I think that should fix our logic. So we're not adding rotting tomatoes to our grid. However, we are allowing a rotten tomato to be our seed. Now, that is all nice, but I just came up with a more elegant solution. So we actually don't do this. Instead, we will keep our original logic. And what we'll do instead is, as soon as we add an orange to our initial queue, we're going to mark it as non-rotten. So that when we enter our loop, it doesn't get filtered out. So that should work nicely, I think. And yeah, so that's minimal changes. Let's roll back the debugging output. And we are now getting the output of 5, which is good. So we're on the right track, even though we're getting an off by 1 error. And that has now to do, I think, with the fact that we're starting with a certain number of rotten tomatoes, and we mark them as not rotten. So when we're on our little loop here, we will count them as time that expired. So we're going to return instead the maximum of 0 and the result, and we'll initialize the result with -1 to counteract the first step. What? Expected -1 on this example? Oh, return result if result larger than or equal to 0. Otherwise, we're going to return -1, right? That was what we should return when there's nothing to do. Is that correct? Oh no, we have different edge cases. So, okay, so that makes it slightly more difficult. Should I repair this? So we start with the result like that, like so. And if result, oh yeah, I didn't check the edge cases fully. So let's try to understand them. When do we return -1? The orange in the bottom left corner, row 2, is never rotten because rotting only happens 4 directionally. All right, so we should return -1. Oh yeah, we're not checking if it still has any fresh cells, right? So we have to do that. If, well, and how do we do that? Well, we iterate over our little thing here, and maybe we create a little helper function for that. Dev has fresh oranges. Well, we're going to do our little iteration thing. And the fresh orange is the value 1, right? Then we return true. Otherwise, we will return false. Right, 1 is a fresh orange. So if it has fresh oranges after we do all our thing here, if has fresh oranges, return -1, else return result -1 to counteract for the initial counting. Let's see. Yes. All right, so that fixed it. Yeah, so apologies for slightly going off the rails here. So we maintained our approach. We have our queue initialization phase. We then use a BFS to traverse the grid. And we used a little trick where we marked rotten oranges as non-rotten so that we have an easier time when we execute our BFS. At the same time, we need to counteract this setting of a rotten orange to a fresh orange in the beginning by subtracting 1 from the result at the end. So yeah, that's the conclusion. I guess we have to submit it to see if it passes all of the tests. And it doesn't, which means, another edge case. So, right, so we probably should do, after this, we should do another test. If as fresh oranges, there's nothing to do. Because output -1. Wait, why does this return -1? It has fresh oranges. Has fresh oranges. If it's 1, we return true, but it contains 0. Otherwise, we return false. It doesn't have fresh oranges. Oh, because our result is 0. That's why. Otherwise, return result. Okay, so that's another edge case I didn't think about. So it could be that we have no fresh oranges after we set them, that the rotten ones to fresh. So if it doesn't have any, we just return 0. I'm liking my approach a little less now compared to before. So let's see, if I do this, a grid equals that. Let's just run this little test without submitting the entire thing. And now we are getting 0 as we want. All right. All right, so we can now see that this approach with setting them to fresh adds another edge case that we need to evaluate before we start traversing the grid. So let's submit this. Fingers crossed that it passes, and it does. Okay, cool. Alrighty. Yeah, maybe you have a better way of doing that. That doesn't require, you know, these edge case kung fu. I don't know. Well, luckily we fixed it, so, and it works. That's what counts. On to the next one.